I'll go ahead and get started. Hi, everyone. It's been a little while since we've seen each other, so I hope you all had a good Thanksgiving, and I hope you have caught up on your email backlog since returning to work. I know that's been a big priority for me. So anyway, today, this is the Process Study and Model Improvement panel. We are hosting Caitlin Whalen. And she will be talking to us about an upcoming project she has to study ocean mixing in tropical instability waves. Just a little bit of background on Caitlin. She is a senior oceanographer and affiliate assistant professor at Applied Physics Lab at School of Oceanography at the University of Washington. Caitlin earned a bachelor's degree in physics from Reed College in Portland, Oregon. She earned a PhD in physical oceanography from Scripps Institution of Oceanography, worked as a postdoc at APL for a little while before starting her current positions there. Caitlin has apparently been fairly busy during the pandemic. I think I counted 6 lead or co-author publications during 2021, so congratulations, Caitlin. Other work that she's been involved in, she has several publications focusing on ocean mixing and various other ocean processes. 2 publications of note. In 2019, she was a contributing author to the IPCC Special Report on Oceans and Cryosphere in a Changing Climate. And in 2021, she authored a paper entitled Best Practices for Comparing Ocean Turbulence Measurements Across Spatio-Temporal Scales. So this really touches on some of the themes that we've been discussing a lot recently as a panel. So I think what she has to talk about will be of interest to her. I also know Caitlin has been involved in our field's diversity, equity, inclusion efforts going back to 2012. So that's always nice to see leadership in that area. And finally, Caitlin spends a lot of time at sea as a seagoing oceanographer. She has participated in field programs everywhere from the Indian Ocean, tropical Pacific, Bay of Bengal, Southern Ocean, and North Atlantic. And I counted up since 2009, she has accumulated 252 days in total, which is nearly 3/4 of a year. So, so this is great. I'm really looking forward to what you have to present to us today, Caitlin. And with that, I will pass it over to you.
Thank you, Charlotte. Yeah, I didn't realize I spent that many days at sea. I learned things from my own introduction. Okay, thank you for the lovely introduction. So today I am going to be talking about an upcoming project that has been funded from via the NSF. And my co-PIs on this project are Amy Waterhouse and Gunnar Voigt, both at Scripps Institution of Oceanography, and also Jim Moom at Oregon State University are also involved in the project. And we are excited to do field work in 2023 and 2024. And the title of this project is called Evaluating Mechanisms for Enhanced Mixing Below Tropical Instability Waves. So if any of you need a refresher on tropical instability waves, they exist because you have a cold tongue along the equator during La Nina periods and also neutral cycles. And especially in the Pacific Ocean, it's really prevalent. And along that cold tongue, you see these cusps of eddies that are propagating to the west. And those are tropical instability waves. And they're strongest during strong La Nina periods where you have a really strong cold tongue. And then they're weaker when you have weaker cold tongue along the equator. And so what I find interesting about these waves, one of the things I find interesting is that when you go out and you take measurements in kind of along one of the propagating fronts of these tropical instability waves, so kind of the part of the swirl that is leading as it's propagating across to the west, what you see is, at least in these observations, is you have alternating bands of shear below one of these fronts. And that's really interesting because it's indicative of possibly internal wave activity or some sort of smaller scale features below these sorts of fronts. And so that's suggestive that we may have turbulence and mixing associated with these features as the tropical instability waves propagate across. And so seeing this suggests that there may be some interesting mechanisms that could cause turbulent mixing, which may change the vertical heat flux along the equator and may play a role in enso cycling along the equator. So it could be pretty important. Another piece of evidence to suggest that there could be elevated sort of small scale features or internal wave activity that are associated with tropical instability waves is this plot over here. So along the x-axis, you have the longitude, and then time is on the y-axis. And then the colors are a measure of essentially a proxy for internal wave energy. So it's the kind of the variations that in the vertical strain fields on scales between 40 and 100 meters or so. And this is averaged kind of on a band between 2.5 degrees south and 2.5 degrees north, and it's looking at the range between 400 and 600 meters. But if you kind of fiddle around with the range, you can still see the same pattern. And what's interesting is that you see um, elevated proxy for internal wave energy that propagates across the equator. And that is the strongest when you have strong La Nina cycles. So we have a ENSO index along the side. And during La Nina periods, you have these strong propagating regions of internal wave, possibly internal wave energy that propagate across the equator. And that's interesting because that would indicate that when you have strong tropical instability waves that are propagating across the equator during La Nina, that's correlated with these strengthening of the internal wave fields. And another clue that links all these pieces together is that we can estimate the diffusivity using a method that has a number of many different caveats, but you can use it as another clue for what's going on. And you see if you average during La Nina cycles in the middle of the Pacific Ocean, you have larger estimated diffusivities that are significantly larger than during El Nino. So the La Nina is significantly larger than the El Nino. So the idea is that there may be internal wave activity that could be causing elevated turbulent mixing during La Nina than El Nino, and that turbulent mixing could help mix heat vertically along the equator, which would be really interesting to sort out. So that's kind of the general motivation of the project. We have all these clues that there may be modulation of the internal wave field due to tropical instability waves. And we want to sort out what might be happening. So we have three different mechanisms that kind of are based on previous work that we are using to kind of drive our science. And but before I talk about those, I'll discuss kind of the guiding questions that are framing all of the science that we're doing. So the first is, what processes govern the observed modulation of internal waves and possibly turbulent mixing by tropical instability waves in the equatorial Pacific? So we're kind of looking at the process level part of the whole thing. And then I think it'd be really awesome if we can also address the question, do these processes play a large enough role in heat regulation to be significant in ENSO dynamics? So this is a kind of a reach question, but I think kind of posing the reach question is at least helpful for me to figure out the smaller steps we need to get there. So framing the small questions in terms of what our end goal will be. All right, so the first mechanism that might be important here is essentially the idea that tropical instability wave fronts, as they're propagating along to the west, could be depressing isopycnals. And when they're depressing isopycnals as they're propagating, they could generate a wave. So this is similar to a Lee wave activity that you may be familiar with, where you have a mountain and then you have flow over the mountain. And as the flow goes up and then over the mountain, it will generate a wave due to the displacement of the isopycnals. And so it's kind of the same thing, but upside down. And the thing that's moving is the mountain or the tropical instability wave front. And so this paper that these figures are from show through a modeling study that it can generate a passage of a tropical instability wave front can generate a wave that satisfies a dispersion relationship that you'd expect when thinking about Lee waves. And so here's the wave that propagates downwards from the tropical instability wave front. So this is one idea of what is happening. You may see these waves might be generated, and that could be interacting with other waves in the field or just causing more elevated internal wave activity, which can be funneled down to smaller scales and cause turbulent mixing. The second mechanism that we're considering might be important here is sort of the loss of coherence and the scattering of existing waves in the ocean along the equator. So the idea here is you may have waves generated by tidal flow over bumps in the ocean. So here's one example of a ridge off the equator in the Pacific. And as the tides slosh over the ridge, they can generate internal waves, which can propagate away. And this is the coherent energy flux from a ridge in the Pacific Ocean. And then as they cross the equator, the jets and or possibly the tropical instability waves passing over the equator could cause those waves to become incoherent and can scatter off different features as well. And so you have a larger incoherent internal wave energy flux as you cross the equator. And as the waves are modulated by things and they change, that can cause them to, or help them go to smaller scales and eventually cause mixing. So it can be one step in the internal waves to smaller scale internal waves to mixing progression. And so that could be, so this process can be facilitating more vertical turbulent mixing along the equator. So, and part of that might be due to the large number of fronts crossing the equator. Or not fronts, but jets. So here's a nice cross section of the equator in this, close to this region. And you have all these alternating jets crossing the equator. So that could be causing part of the incoherence. And the other idea is that during months where you have stronger tropical instability wave activity, you see a larger loss of coherence along the equator. So the thought is that these tropical instability waves could be causing these other internal waves to lose coherence and possibly go down to smaller scales. So that's mechanism 2 that might be important here. And the third mechanism is kind of on the smaller scale end of the whole internal waves to mixing progression. And this is the idea that the tropical instability wave front or the jets along the equator could be really strongly influencing internal waves, and to the extent where they essentially break and turbulently mix the water. So if you have really strong gradients in the vorticity of the background flow or the kind of horizontal or vertical shear of the flow, then you can have strongly influenced internal waves, which can really go down to smaller scales and cause dissipation. And so on the left, you have observational evidence of this along the edge of an eddy. So possibly it's going to be happening along one of the edges of the tropical instability wave eddies, which kind of make up the the swirling part of the wave. Or on the right, you have modeling indications that they could be happening along the edges of the jets along the equator as well. So kind of this is mechanism 3 that we'll be looking at, thinking about how the unique dynamics of the tropical instability waves and the equator could be influencing the progression to turbulence, and then also if thinking about if that would be enough to modulate the vertical mixing along the equator. Okay, so I talked about the kind of motivation, the guiding questions, and then a bunch of different mechanisms. So the next thing I'll do is lay out our specific hypotheses that we're hoping to address in this particular study. So the first one is as they propagate westward across the Pacific, tropical instability waves radiate internal waves, which propagate downwards, elevate local internal wave activity, and local turbulent mixing. So that's essentially the mechanism 1 that I discussed, so the Lee wave mechanism, that Lee wave-like mechanism of the tropical instability waves generating internal waves. And then the second guiding hypothesis is large-scale internal waves generated elsewhere interact with tropical instability waves, causing a transfer of energy to small-scale internal waves, potentially strengthening the local turbulent mixing. So this is the mechanism 2, where you have existing internal waves interacting with stuff on the equator and facilitating turbulent mixing, which could be significant on a larger scale. And the third hypothesis is after the small scale internal waves are elevated by either hypothesis 1 or 2, they dissipate energy in critical layers. So that's where the internal wave breaks along strong gradients of background flow at the edges of tropical instability waves, eddies, and or equatorial currents. And then the fourth sort of reach guiding hypothesis is the modulation of turbulent mixing by tropical instability waves described in 1 through 3 substantially impacts the vertical transport of heat in the equatorial Pacific over timescales of tropical instability wave periods to seasons. So this is kind of, we're trying here to link all of the processes that we're thinking about to the impact on ENSO and climate. So we're trying to put all of the things that we're learning in the other hypotheses categories and say, okay, is this important for questions on climate scales? Okay, so the instrumentation that we're going to use to do this includes a number of different factors. So we're going to go on 2 cruises, process cruises, and do a year-long mooring deployment. And so the mooring is diagrammed in the left. We'll have 3 moorings, and they'll have CTDs, they'll have Kipods, so that measures turbulence, and also ADCPs on the moorings, and the other tools we'll use would be the fast CTD from Scripps, and it's a fast, this as you would expect, it's a CTD that goes up down really quickly in the water column, and it's really good for measuring small variations in the ice thickness over really short timescales. So for example, internal waves. And then the third tool we're going to use is a wire walker. And so this is great. It has a weight at the bottom and then a float on the top, and it drifts around and has a line, and uses the wave energy to ratchet down and then buoyancy to go up. And it has lots of different tools on it, like a CTD and measuring turbulence and measuring velocity as well. And so those are the 3 kind of main tools we'll be using on our cruise. And then kind of the way we're thinking about our science plan here is we're going to put out the 3 moorings, one at 0.5 degrees north, one at 1.75 degrees north and one at 3 degrees north, and that hopefully will capture the kind of the bottom half of the tropical instability wave eddy as it goes through the area. And the idea is to deploy the wire walkers on either side of a tropical instability wave front. This is not to scale, by the way. So we can see the lateral differences across the front, and that will be really helpful in determining kind of the different mechanisms that may be at play. And then we have a number of different modules that we're hoping to use to profile with the fast CTD. So we may use cross-front transect. So you may, as the front is propagating, kind of go back and forth along the front in the reference frame of the propagating front, and do a bunch of different transects across that. We may also do something like a box, doing a little box survey, so we have some lateral variation across one of the tropical instability wave fronts, or we may just sit in one spot and watch as the front passes. So we'll probably modify exactly what we're going to do as we're out there and see what we're seeing with the incoming data. Okay, so I think from what I understand, this panel might be interested in how we're thinking about using the data as well. So I thought I would lay out our plans for analysis slightly as well. Obviously, they'll probably change once we get the data coming in. So we have a number of different analysis trajectories, and the first is using the mooring data to look at the seasonal cycle and shear mixing due to tropical instability waves. And so this will be really helpful in connecting the smaller scale processes with the longer time scale, and thinking about the implications for climate using that linkage. And so we're hoping to look at the seasonal cycle in the tropical instability waves and the associated internal waves. We're hoping to kind of distinguish between hypothesis 1 and hypothesis 2. So thinking about either whether the internal waves that we see are generated by the tropical instability waves, or if they are possibly modulations of existing waves. So this data will help us distinguish what is more likely, or a combination of them. And then we'll also be able to link the internal waves that we see with turbulent mixing due to the turbulence sensors in the moorings, and look at the seasonal cycle of that. The second kind of trajectory will be focused on one of the fronts, and that will be using the fast CTD data. And we'll be able to calculate things like energy fluxes, and so that'll be helpful for figuring out if waves are actually coming from the fronts or coming from somewhere else. And we'll be able to kind of dial in on looking at the critical areas where the waves are arrested right at the fronts themselves. And we're gonna hopefully be able to quantify if the dissipation that we're seeing is actually enough to be important for larger time scales and larger spatial scales, like the dissipation of the energy of the tropical instability waves, for example. And then for the wire walker data, we'll be able to really get a great lateral understanding of how either side of the front is behaving. And so that will be helpful in distinguishing if it's a wave that's being generated by the front. So that will have like a phase difference between both sides of the front. Versus if a wave is coming in from elsewhere, we won't see that phase difference. And we'll be able to get a sense for the vorticity we'll have 3 rotating wire walkers, and we'll have a measure of the vorticity on that scale, which will be helpful in thinking about how the vorticity could be modulating internal waves from elsewhere. And yeah, and then the final piece of analysis is explicitly connecting what we're observing to the larger time and length scale questions. And so we're going to estimate the vertical near equator heat flux in the thermocline and figure out its divergence and how it's modulated seasonally, and try to connect that with the different processes we're seeing. And so looking at if we see changes in the vertical heat flux that are associated with certain number of the processes we're evaluating in the previous analysis steps. And so this analysis step might be challenging, but it also might yield really interesting results. So I'm super excited about that, hoping it'll work out. Okay, so in summary, for this project, we're interested in how tropical instability waves are or could be modulating turbulence and vertical heat flux and internal wave activity kind of below the surface layer in the ocean, so roughly in the thermocline region. And we have two guiding questions. One is what processes govern the observed modulation of internal waves and possibly turbulent mixing by tropical instability waves in the equatorial Pacific? And the second guiding question is, do these processes play a large enough role in heat regulation to be significant in enzodynamics? And so that is pretty much the summary. We'll be using a bunch of tools, so moorings, fast CCD, and wire walkers, and we're trying to sort out what processes might be important for connecting the internal wave activity to mixing to climate scales. Great, so that's all I have today, and be happy to take questions or suggestions or notes of connection.